So our final example of using binary variables within a mixed integer program or an integer program is called the assignment model. Here what we're doing is we're assigning exactly one job to one person and one person to one job. So one-to-one correspondence. So in this example, you are the hiring manager at an accounting firm headquartered in New York City. You've recently hired 3 new USM graduates and must decide at which regional offices to place them. However, there's also an opening in New York City, and you're willing to send one of them there if that relocation is more economical. Using the data on the next slide, what is the optimal assignment of personnel to offices? So here we have Smith, Jones, and Torres. We have an office in Omaha, Charlotte, and Cincinnati. And to send Smith to Omaha, it costs $800. To send Smith to Charlotte, $1,100. To send Smith to Cincinnati, $1,200. Jones, $516, $13. Torres, $500, $1,000, $2,300. Additionally, it costs $1,000 to relocate Smith to New York, $800 to relocate Jones there, and $1,500 to move Torres to New York City. So in these, we either have a balanced or unbalanced problem. A balanced problem would mean we'd have the exact same number of people as we have offices in this case. This is unbalanced. We have more places to send people than we have people. So we have 4 offices in New York. So what we really could do is off on the right over here, add New York and put in 1,000, 800, 1,500. And what we want to do is that means one place will not get a person, right? So luckily for us, we can easily handle an unbalanced problem just as easily as a balanced problem in Excel. So this is going to be set up a little bit different than what we've seen before. Here, the variables that we're going to define are going to be subscripted by 2 indices. It'll be the person and place. So I might have something like XI, XSO. So that would mean yes, I'd put a 1 there if Smith goes to Omaha. 0 otherwise. So that means we're going to have 3 times 4, because New York City's out here. We'll have 12 different variables, right? And then we'll have to look at how to do the constraints. So let's go to Excel and see if we can get some of this working. Let's see here. All right. So this is going to be quite a bit different than what we've seen before. We're going to have Omaha, Charlotte, Cincy, and New York City. And here we have Smith, Jones, and Torres. Right? And we're going to have these 4 as our decision variables. So I'm putting them in a grid instead of 12 across, mostly because it's a lot easier to keep track of this way. Right? There's nothing stopping me, and because I'm indexing it by 2 indices, this is a variable here. Right? So the next thing I'm going to do is I'm going to go down here and put this guy here and these guys here, and then I'm going to put in the costs, which was on that last slide that we just saw. So this is $800, $1,100, $1,200, and then 1,000, which I got from that sentence there. Jones is 500, 1,600, 1,300, and 800 for New York City. And then for Torres, it's 500 to go to Omaha, 1,000 to go to Charlotte, 2,300 to go to Cincinnati, and 1,500 to go to New York City. So then, let's see, the next thing we need is an objective function. I'll put it up here. And what we've been doing has been using sum product. We're going to use sum product again, but this time we are going to use it over multi-dimensional array. So B2 through E4. And I can do it as long as the arrays are the same dimensions. I can do it for those guys right there. And we see right now that this is just $0. So for example, if I put Smith to Omaha, Jones to Charlotte, and Torres to Cincinnati, it would cost $4,700. This would mean no one goes to New York City. Right? So you could play around with that a little bit if you wanted to. Alright, so now we need to set up the constraints. The constraints are slightly different than what we've seen before. Here I don't have a variable in each column, right? I have variables over rows and columns. I have a total of 3 times 4, 12 variables up here in blue. My constraints, however, I have a constraint for Smith, one for Jones, and one for Torres. That constraint is saying that we want to make sure that Smith only goes to at most one place, right? So we're going to say we can use, let's see here. So again, what we're doing here is that each Smith, Jones, and Torres can only go to one place. So that'll be the right-hand side, the constant, the number on the side. And then here we want to put an equal sign, right? I'm putting an apostrophe in front of it so it looks at it as text, just so I can see what it looks like, right? So we're going to say Smith goes to exactly one place. I don't want to send Smith to more than one place, right? So then the left-hand side, in this case, we just need to add up, do a sum over all the places that Smith could go. So she could go to Omaha, Charlotte, or Cincinnati, or New York City, right? So if I do that, right now she's not going anywhere. Scroll this down, right? And so Jones, so we're adding up all of the variables on that particular row, that person. Now, the other part that we have to look at each city. So each city gets at most one person. So Omaha can get 1 or 0. Charlotte can get 1 or 0. Cincinnati, 1 or 0. New York City, 1 or 0. So we'll have to do it that way, right? So let me do left-hand side, right-hand side, and we'll do less than or equal to. We're doing less than or equal to because we have more cities than we have people. And again, we only want one person to go each place, or each city to get at most one person. This time we're going to add up for a column. So Omaha, and then we ought to be able to drag this over. Right. So this we're using sum instead of sum product like we have been using, but that's okay. Right. So now I think we're okay. So let's go and try to solve this thing. So I'm going to click on G2 and go to Data, Solver. I am minimizing my objective function, which is in G2, by changing these 12 variables, B2 through E4, subject to, and again I have two sets of constraints. I'll do the people one first. Those guys, strict equality, the right-hand side, add, and then over the cities, the left-hand side, that's less than or equal to 1. Click OK. And I'm going to try again, because I like to try this, running it without putting on integer constraints and see what happens. So click Solve, click OK, and voila. We were able to get out integer variables and binary like we were trying to do. So this is a very special form of a linear program. The assignment model is very special. I have a totally unimodular matrix, so it allows me to get integer answers for free as long as the right-hand sides are integer. Alright, so what is the answer? Poor Torres has got to go to Omaha. That shouldn't surprise us. Look how cheap it is to send her there. Charlotte gets Smith. New York City, Jones goes there, so no one is going to Cincinnati for a total cost of $2,400. Right? So that's the absolute best that we could do. So that's the assignment model.